Hi, everybody. Welcome to the first day of the Distributed SQL Summit's workshop day. And we're going to talk about an introduction to YugabyteDB, its design and architecture. And I'm Karthik Ranganathan, one of the co-founders and the CTO. Okay, let's jump right in. First off, YugabyteDB is a distributed SQL database, right? And it makes sense that this is the Distributed SQL Summit and we're discussing distributed SQL databases. So what is distributed SQL? Well, distributed SQL is a new database architecture that retains the power of SQL and ACID-compliant transactions and all of that, while offering resilience to failures and high availability. It offers massive scalability, which means you should just simply be able to add nodes in order to scale out horizontally. And finally, it offers features around geographic distribution. By geographic distribution, what one can think of is a multi-zone deployment, a multi-region deployment across clouds, or a hybrid topology, and so on and so forth. So deployments that require different types of fault domains, as well as having to bring data closer to the end users or partition them geographically for some purpose, right? And this could be to really give lower latency access to the end users, or for regulatory and compliance reasons, like you need to keep all of the data generated by users in a particular country inside that country, right? And the overall reason why distributed SQL exists is that modern applications are being built with some of these features as requirements, which is resilience and high availability, scalability, geographic distribution, to run in cloud-native environments. While the traditional RDBMS, which gives you all of these features required to build these apps, are not really cloud native, right? It's an enormous amount of effort trying to bring those databases to run in a cloud native fashion. So the emergence of distributed SQL really fills that gap. Okay, so now that we've looked at distributed SQL, let's take a look at specifically what YugabyteDB does. YugabyteDB is, of course, a distributed SQL database with a focus on high performance and low latency. It has a focus on being cloud native, so you can run it literally anywhere on any IaaS, be it Kubernetes, VMs, or bare metal. And it's completely open source under Apache 2.0, very similar to PostgreSQL. So we talked about distributed SQL databases or distributed databases, right? So it's important to distinguish what monolithic databases do vis-a-vis distributed databases. Monolithic databases typically serve reads and writes from a single node. If you need more resources, you simply scale this node up. Now, if that node that had the database data in it failed, you would not be able to serve anything as is, right? And externally, as a person or an operator, you'd have to fail over to another standby database that can now take all the reads and writes. So inherent to the database, it cannot tolerate failures and therefore cannot ensure high availability. And finally, the rule of thumb is always to normalize data, not only for consistency, but also to save space. And the reason for this being, if you run out of space on a single node, the process to scale up is really complicated. And if you cannot scale up anymore, which means you have one of the biggest nodes around, besides it being expensive, it becomes really difficult to rewrite your entire application to shard your data across multiple nodes. Now, in contrast, distributed SQL databases can serve writes across multiple nodes. So they will have multiple nodes in the cluster, which will kind of seamlessly look like one logical database to you. You can scale this cluster out horizontally simply by adding nodes, and they can tolerate failures to any node by redistributing the queries across different nodes and re-replicating the data to different existing live nodes. And finally, you have the option to not just normalize for the purpose of consistency, you can also denormalize data for improving your performance, right? Be it throughput or be it like your latency on access. Now, we talked about what distributed SQL databases can do, and one of those items was scaling out, right? So now let's look at how distributed SQL databases scale data out. In the case of distributed SQL, no single node holds all the data, right? So in the diagram that you see below, the data gets sharded or split into multiple chunks. So if you take a logical table of a user, like let's take a single table, then you split the table by a group of rows, And each group of rows in this case will be a shard, and you distribute these shards across different nodes. So this achieves the ability to distribute data across nodes. Now, the second step to tolerating failures in this scaled out system is to make sure you have replicas of data on other nodes, right? So this means that if a particular node goes down, the replica is present in other nodes and they can take over and start serving the data. Now, in order to do that, you replicate the data at the shard level across different nodes. So in the previous diagram, we had shards 1, 2, 3, 4 assigned to nodes 1, 2, 3, 4. In this diagram, you note that shard 1 is replicated on shards 2 and 3, the data of shard 1, and shard 2 is replicated and so on and so forth. So in this example, with 4 nodes and replication factor 3, we have all of the data of the table replicated 3 ways and evenly distributed across these 4 nodes. Now, if any node fails, let's say node 1 fails, then you note that shard 1, which was being serviced by node 1, can quickly fail over to nodes 2 or 3 because they are a live standby and they have copies of data. So you're able to lose one node and immediately continue functioning because shard 1 has 2 other copies. Now, if you wait for a little bit of time and the node stays down, you'll find a different location, which is node 4, in order to re-replicate the data. And the system is back up to its replication factor of 3 because the node that failed, its data is replicated to the other nodes in the system. So what you'll note is that you can eventually lose up to 2 nodes and the system would work well in this case. One of the concerns that comes up in the case of distributed SQL databases, which don't exist in monolithic databases, is what happens during a network partition. So first off, what is a network partition? A network partition is a scenario where a subset of nodes cannot talk to another subset. They're kind of partitioned away or they cannot communicate. So in this example on the right, there's a partition that splits right down the database cluster. Now, obviously in a monolithic database, there's just one node, so it falls on one side or the other side of the partition, and the client can either reach the node or not. And you're fine either way, right? In one case, you have unavailability. In the other case, you have you're just functioning as normal. Now, in the case of a distributed database, if there's a partition across the nodes, you have some clients which can reach the node on the left, and you have other clients which can reach the 3 nodes on the right. So this forces the question of, do you choose availability, which means do you serve data on both sides, or do you choose consistency, which means do you stop serving data on some sides? Because it's important to figure out what we want to do. Now, because SQL databases and single node databases are known for their ACID compliance and consistency, a distributed SQL database has to make a similar choice of siding with consistency. But this brings us to the famous CAP theorem, which says that if you have to choose between consistency, availability, and partition tolerance, you can only have 2 of these 3. Now, the scenario we're talking about is partition tolerance, and it's extremely important to the fundamentals of running this as a logical SQL database, right? A cluster of nodes as a logical SQL database. So it's important to note that in the face of network partition, the choice really comes down to, do you want to opt for consistency or availability, since you cannot have both? So Yugabyte opts for consistency and reduces availability, right? But the question is, can we make the availability high enough that in practical situations, this does not really affect you, right? So what Yugabyte does is it allows for a failover in a matter of seconds in, for example, a multi-zone deployment in the cloud. So this means that your availability is high enough to not really be the bottleneck or to be the single point of failure in your system. The system quickly and automatically recovers from such partitions in a reasonable period of time, which manifest itself as elevated latencies or very temporary set of failures. So how does Yugabyte actually behave? So if you always start out with an uneven number of replicas. In this example, we have 4 nodes with 3 replicas. Now, if the nodes are partitioned this way, you note that on the left, when a client comes and talks to that node, it cannot reach a majority. The consistency is ensured by making sure any node or any piece of data can reach a majority of its replicas in order to continue to serve queries from the end user. Now, because you cannot reach a majority for shard 1, which would have been serviced by the node on the left, you note that all of the reads and writes for shard 1 fail unless you're specifically doing a stale read or a point in time read as of a point in time in the past. Now reads on the right will continue unaffected because each of the nodes there, like the shard 1, the failure of shard 1 on node 1, which cannot be reached, will cause one of the other nodes that contain shard 1 to become the leader, and all of the shards can be serviced by the nodes on the right. So client on the left will experience failures, client on the right will just continue fine. This architecture that we talked about is actually really similar to Google's Spanner, which is also a CP system, or a consistent and partition tolerant system with high availability. Now, the next topic to talk about is, what do you do if you are trying to update multiple rows? Because we split the table by rows and we distribute them across nodes and replicate them and so on, obviously updates to a single row will fall on a single tablet, which replicates data using a consensus protocol like Raft, like we saw in one of the previous slides, and will have its consistency. Now, what happens in the case of a distributed transaction? Well, the idea is what Yugabyte does and what all distributed SQL databases do is to allow you to perform all of these writes to individual operations inside a transaction and eventually make everything visible in an all or nothing fashion. So it has to be atomic, right? And with consistency. Now, the way this happens is really by using a two-phase commit internally, where the transaction actually performs a lot of provisional writes that go to the various tablets or to various shards and write each of the pieces of data. And once all of those provisional writes are successful, then the entire transaction is flipped to being visible, right? At which point it starts getting served. Note that YugabyteDB supports snapshot isolation and serializable, right? So the YugabyteDB has two APIs. We'll talk about that in a little later, but one of the APIs, which is YSQL derived from PostgreSQL, supports both of these isolation levels, while the other API, YCQL, which is derived from Apache Cassandra, actually supports only serializable snapshot isolation level. All right, so with that overview, let's actually dive into how Yugabyte gets deployed across nodes and how its architecture looks. The first set of concepts is the notion of how a cluster and a universe looks. So in this example, if you have a replication factor 3, you need a minimum of 3 nodes, right? Like, because you need 3 copies of the data. If you have a replication factor 5, you'll need 5 nodes minimum. Now, your nodes itself can be VMs, containers, bare metal machines. It doesn't matter. It's just some compute with storage attached to it and some RAM. Now, all of these nodes together is called a universe. A universe internally can be comprised of one or more logical clusters. A cluster is a grouping of nodes that stores data and handles end user queries. Now, in this diagram on the right, you find that the 3 nodes on the top, which form the primary cluster, actually have a user table that is sharded and replicated across these 3 nodes, and will handle all the reads and writes from the end user client. Now, it's possible to asynchronously replicate these tables or this data in this cluster into other clusters, which are read replica clusters that only serve reads. All writes going to the replica cluster will be redirected to the primary cluster, which will then perform the write and re-replicate it back to the replica clusters. The replication from the primary to the replicas is asynchronous, which allows for a lower write latency because you don't have to wait for the data to replicate to all of these remote clusters, while giving you low read latency, whether you read from the primary cluster or the replicas. Of course, if you read from a replica, you're reading data that's a little bit stale. All right, so let's talk about a single cluster. So let's take the primary cluster. In the primary cluster, there are 2 types of services inside the system. The first service is a YB-TServer, which hosts and serves user data. In this example, you see that every node in the cluster, which is each of the 4 nodes, has a YB-TServer process, all of which join to form a YB-TServer service. The second service that runs on the system is called the YB master. The YB master is the control layer. I mean, again, it's not exactly the best name. It's something that we're working on changing. But the YB master can be thought of as a cluster manager, which takes care of the cluster-wide operations and stores the metadata for the entire system. Now we look at this in a little bit more detail in the subsequent slides. On the T-servers, what you note is that every node that has the T-server internally contains a query layer, a distribution transaction manager, and all of the tablets that belong to the various tables. The tables themselves are split into tablets. The tablets are replicated. Each node has what is called a tablet peer, or a copy of the tablet. Now the client interacts with the query layer, which then uses the transaction manager to address all of the data to fetch whatever data it needs or performs writes. Now the tablets in blue here are the tablet leaders, which serve strong reads, and the tablets in orange are the tablet followers, which serve timeline consistent reads, and in case of a failure can take over and become a new tablet leader. So T-servers, once again to recap, deal with all of user data and serving user I/O. YB masters, or the cluster manager on the other hand, manages the system metadata. So every time you create a table, you need to store schema. It has a bunch of tablets, the set of nodes, the replication assignments, etc., etc. All of that is stored in the YB master service. Note that the YB master service is also replicated and highly available and fault tolerant. So it is also a service that is not a single point of failure in the system. The YB master is also responsible for doing things such as load balancing. We talked before that if a node is down for an extended period of time, its data is automatically re-replicated into another node if one is available. So the YB master service is responsible in order to make that happen. So it waits to hear back from nodes, and if a node doesn't check in with the YB master in a particular length of time, by default it's about 15 minutes in Yugabyte, then it finds another location for that piece of data in such a way that it still satisfies the replication constraints across fault domains and brings up the replication factor of the system back to where it needed to be. Now, we talked about replication and fault tolerance and all of the different API layers that you can come through. Now, one of the key aspects is how you shard data. This is not a concern for a traditional single node RDBMS because all of the data resides in a single node, but becomes more critical in a distributed SQL database because you spread your data across nodes and use your tablets or your sharding mechanism in order to spread data. So the way this works in YugabyteDB is you have a couple of different sharding strategies. The sharding is determined by a subset of the primary keys. So a row could have a multi-column primary key. A subset of those rows or a subset of the composite primary key actually determines how data is distributed across these nodes. There's a couple of different strategies in determining how this happens. The first one is hash sharding, where you pick a random set of rows from from the table and you put them on a node. So that's the example shown in that's the diagram shown on the right. Or you could do range sharding, where the data is lexicographically sorted and each tablet is really a contiguous set of rows of the original table, which allows for better range queries. Hash sharding allows better distribution of data and eliminates hotspots, while range sharding allows for range queries. On the replication side, each tablet or each split that we discussed in the previous slide is actually replicated across different nodes. The tablet peers form a raft group, and the peers replicate data synchronously using a consensus protocol. Right. So the way this works is the tablet leader, which is in this example on node 1 for tablet 1 peer 1, receives the write request, and it sends the write request to itself to the node 2 and node 4 and waits for a majority of these three to commit the data. So itself and one other node minimally to commit the data. Now, once you get the ACK from a majority, once the data has been persisted successfully on a majority, this system acknowledges the end user write, saying it actually finished the write in a durable fashion and can survive failures. Now, these replicas and nodes can actually span racks, regions, cloud providers, zones, what have you. So it gives you the ability to tolerate larger level failures, like more catastrophic failures, because your data can be persisted across fault domains. The consistency of reads can definitely be relaxed by reading from some of the followers. The consistency on writes for the primary cluster is always strongly consistent. However, you can have read replicas and asynchronous replicas, which will asynchronously replicate data, which relax the consistency and give you better performance. Now that the data is replicated across different nodes, the next step is the storage layer, how data is actually stored on disk. Note that YugabyteDB is optimized for SSDs. So it expects like an SSD to work on. It wouldn't be very optimal to run YugabyteDB on hard disks. YugabyteDB internally stores data as documents. So it provides at the storage layer a persistent key to document store. It's built by extending RocksDB into and converting it from a key to value to a key to document store. Now, every row in the original table really is comprised, every SQL table, right, like consists of a set of columns in a row that determine its primary key and another set of columns which are simply the value columns. The primary key columns map to the document key and the value columns map to the document attribute values. So this is shown in the diagram on the right, where you have a table which has artist, year, and song as the primary key, and you could have a whole bunch of other like value columns. And artist is determined to be the partition key, or the way you distribute data across nodes. And so all of the artists with a certain value will go into a single tablet as shown, and the sort order is done like on the year and the song, right? It could be ascending or descending, really depending on the order that you choose when creating the table. All of the value columns are stored as a document against each of these keys. The next thing that YugabyteDB supports is secondary indexes on top of these tables. And the way that works is a secondary index is really another internal table, which is a distributed replicated table with all of the properties we talked about. And every time you do an update to the primary table, and if the table has a secondary index, this results in a distributed transaction where you insert the row into the primary table and insert a row into the secondary index. Those will still be provisional writes. And once all of those have been done, then you go ahead and update the transaction to become visible. Now, in the case of a pre-existing row and you update a table with an index, it would result in updating the primary table value with a provisional write, and then deleting and inserting a new value for the index table as provisional writes, and finally finalizing all of those as a part of a two-phase commit. The query layer of YugabyteDB is extensible, right? It's been built to support multiple APIs. This is quite similar to Amazon Aurora, which supports PostgreSQL and MySQL. YugabyteDB supports YSQL, which is PostgreSQL compatible. So it's fully ANSI SQL relational API. It can be scaled out as an RDBMS API, and you can do a lot of relational integrity, like constraints, etc., like foreign keys and check constraints and so on and so forth. You can do joins, triggers, stored procedures. It's compatible with most of the features as of now that are present in Postgres 11.2, or a lot of features, and work is underway to move this baseline over to Postgres 12. And the YSQL API is a semi-relational API, which is for massive scale applications that need really low latency access. It supports most of like the data types and columns, etc. It supports indexes. It supports unique indexes as well as JSON, document data columns. But it does not support a lot of referential integrity or joins in order to, or things like triggers and procedures. And the idea is really to keep the set of SQL supported really simple in order to ensure that the performance is really high and you can make a lot of internal optimizations that give you low latency access. Now, irrespective of the API, clients can connect with drivers in many languages. For example, Java, Python, Node.js, Go, etc., etc. So there's a number of different client libraries. And depending on the API, the YSQL API are mostly traditional vanilla PostgreSQL drivers as of now, while the YSQL API is cluster aware in the sense it's aware of the set of nodes in the cluster. It's aware of topology, so you can do reads from the nearest data center. You don't need a load balancer in order to interact with the database and so on. Now, if we go quickly into how the YSQL API was built as just like a way to double click on exactly how the system works. Well, this is a very high level view of PostgreSQL where you have, postmaster, rewriter, planner, executor, optimizer. And the aim here was to reuse the upper half of Postgres, which is most of the thing that deals with the query and comes up with the execution plan. And all of the stuff that writes to the single disk, all of those utilities have been replaced, including the disk itself, with a distributed table store called DocDB. This is the document layer, the underneath distributed layer of YugabyteDB that behaves exactly like Google Spanner. Now, in order to accomplish this, we've had to change a lot of the way the planner, executor, optimizer works in order to work with a distributed substrate instead of a single node disk, right? So that's one of the changes that we've had to make. And in this transformation, the upper half effectively becomes stateless. So the system looks like you have a bunch of like nodes, each of which has a process. The upper half of this process is a stateless PostgreSQL, and the lower half is a distributed Google Spanner-like document store, right? So the advantage is now your application can connect to any node, which will internally fetch the data from the right locations. You can add and remove nodes at any point. And failures don't affect you because the lower half is already fault tolerant and it has replicas, it has failover like we talked about. And the upper half is stateless and you simply connect to a different node in order to continue performing your queries. So that's the way internally Yugabyte achieves high availability, scalability, and performance and so on. That's all for today. Please enjoy the rest of the talks and the rest of the tutorials. There's a lot of interesting topics, including GraphQL, like Spring, migrations from different databases, security, how to operationalize and run these databases in production, including dealing with failures, some really cool demos, so on and so forth. So thank you all for joining and enjoy the rest of your summit.